So
Great.
please.
Thank you very much for the invitation. It's a pleasure to be here, and please feel free to interrupt me at any point during the talk. I'm happy to explain more and for this talk to be more informal. So I'm going to talk today about the evaporation of black holes, both in ordinary theories of gravity, like the ones that we have in our own universe, which at low energies looks like Einstein gravity coupled to the standard model, as well as in theories of supergravity in which supersymmetry is not broken. Um, so let me give some motivation about why it's interesting to actually study black holes that have some amount of supersymmetry. So supersymmetry has long served as an important tool towards understanding special black hole solutions that admit not only killing vectors are usually associated to the bosonic symmetries of the space-time, such as rotations, translations, so on and so forth, but also killing spinors associated to fermionic symmetries of the space-time. And recently, there's actually been a pretty big resurgence of studying solutions in supergravity or in gravitational theories that admit killing spinors. And this has helped really understand Euclidean observables that are protected by supersymmetry from the point of view of the gravitational path integral. So unfortunately, I won't have time to talk about that today, but if you're interested, please let me know after the talk. Instead, I'll be talking about a more conventional solution that admits killing spinors, namely the most important example of such a solution is an extremal black hole. In a theory like Einstein-Maxwell theory or in a theory of supergravity, an extremal charged black hole. The idea is that if we take a black hole and minimize its mass for a given charge, this black hole will eventually get to a minimal mass that in the case of a black hole in flat space is given by m equal q, and this equality saturates the BPS bound that this black hole satisfies. And as we approach extremality in the past couple of years, we've learned that what GR plus quantum field theory on a curved background predicts is actually drastically modified. So, in this talk, I'll review what's new about our understanding of extremal black holes. And because these developments are important both in gravitational theories, like the one in our own universe, as well as in theories of supergravity, I'll highlight some developments in both. So about half of the talk will be about non-supersymmetric black holes, and the other half will be about supersymmetric black holes. And I know that last year I gave a talk about non-supersymmetric black holes, so I just want to give you a small refresher about that. So, to start, let's discuss the black holes in our own universe. So, the first natural question that one might ask about these black holes is how does one get close to extremality if you start with an arbitrary black hole in our own universe? So, suppose that you start with a black hole that has some mass m and charge q and angular momentum j. So our goal is to describe how such a black hole evolves over time through Hawking radiation in the MQJ set of parameter. In other words, our goal is to describe what is the evaporation history of such a black hole. Now, um, if the black hole starts with some angular momentum, the first thing that will happen is that it will actually lose most of its angular momentum. And the reason why is because in our universe, as well as in theories of supergravity, there are massless particles that can carry away some of the angular momentum of the black hole. And the black hole has a very easy time emitting massless particles, but a very hard time emitting any massive particle whose mass is greater than the black hole's temperature. The first thing that a black hole will do, and this is something that Page found in the 70s, is that it will emit particles whose angular momentum will be inversely aligned to that of the black hole. And the black hole will quickly lose, well, quickly compared to other timescales in the problem, will quickly lose all of its angular momentum. And here, by losing its angular momentum, I simply mean that the classical angular momentum of the black hole J will go to zero. Of course, black holes, like any other object in quantum theory, have quantized angular momentum. And if I study a black hole in a thermal ensemble, even though the classical angular momentum can be zero, there could be small thermal fluctuations that yield a non-zero standard deviation for the angular momentum. So, as we've established, a black hole in our own universe, if left in full isolation, here I'm not discussing what would happen to a realistic black hole that's surrounded by matter with which it would equilibrate. So, if you left a black hole in full isolation, the first thing it would do is that it would land somewhere in this MQ plane. And to answer what happens next, we have to see how the black hole evolves from here. And there's two directions it could evolve. It could evolve downwards towards this gray line that's plotted here. That is the line on which m is equal to q. So that's the minimal mass that a black hole can have towards at a given charge. It's the extremal bound. Or it could kind of evolve sideways. It could lose some charge, and it could also lose some mass. So the way in which a black hole can evolve downwards is through the emission of neutral particles. And the way in which a black hole can evolve sideways is through the emission of charged particles in our own universe. So for neutral particles, we have massless neutral particles in our own universe, like photons and gravitons. And for charged particles, we have the electron and positron that are charged under the same gauge field as the black hole is, as this hypothetical black hole is. So, to understand how the black hole evolves from here, we can compare roughly the evaporation rate into these two types of particles. So the evaporation rate into neutral particles, if one assumes that the spectrum of Hawking radiation into such particles is roughly thermal, the evaporation rate into such particle is given by a power law in the temperature of the black hole. And if I write that power law in terms of a difference between the mass and charge of the black hole, it's also given by a power law in this difference of m minus q. So this is how the dE dt this is how the energy of the black hole evolves with time. Many times I'll denote E by to be equal to m minus q. So E many times will capture the energy of the black hole above extremality in these formulas. So this is how the rate of evaporation into neutral particles that drive the black holes towards extremality. The rate of evaporation into charged particles, as I said, such particles, when they satisfy this bound, which is also the bound that you might be familiar with from the weak gravity conjecture, particles that satisfy such a bound drive black holes away from extremality. So an example of such a particle is the electron or positron. And because in the surrounding of the black hole, there's an electric field that's due to the charge of the black hole itself, the way in which these particles get created is through a process called Schwinger pair production. So in Schwinger pair production, you produce in a roughly constant electric field pairs of electrons and positrons. Now, as the black hole approaches extremality, the electric field in the near horizon region is indeed roughly constant. And the distance, the distance between the electron and positron at which the Schwinger pair gets created is much smaller than the curvature scales of the black hole. So, as a first calculation, one can roughly use the answer that Schwinger obtained for a constant electric field. And one finds that the decay rate, the Schwinger pair production rate into a charged particle is given by an exponential in minus the charge of the black hole divided by this parameter q star. That's given by the ratio between the charge of the electron and the mass of the electron. So here, whenever you're confused about units, just add the Planck masses to make the units correct. Now, this ratio turns out to yield a very, very, very large number. And because of that, one finds that the production of charged particles is only exponentially suppressed when the black hole has a very large charge. Namely, this Q star corresponds roughly to 10 to the 44 coulombs. And this large number arises because the ratio between the charge of the electron and the mass of the electron in our own universe yields a very large number as well. So if a black hole is above this scale, then essentially it will only produce neutral particles, and exponentially rarely it will produce these charged particles that drive it away from extremality. While if the black hole is below this charge scale, starts out below this charge scale, then the production rate into neutral particles and charged particles is comparable, and the black hole will not approach extremality because of that. I don't know if you can see my cursor, but it could, the trajectory that the black hole can take in the MQ plane can roughly be a curve that stays away from extremality until the charge of the black hole gets very close to zero. Great. So the conclusion of this is that if we start with a black hole that is sufficiently large, sufficiently charged and sufficiently large, then the black hole will just drive itself towards extremality. We don't have to do anything to it through the emission of Hawking radiation. And this is just a consequence of the particle content in our own universe. If we happen to have a massless charged particle, this plot will be modified and we would never get close to extremality. So what happens in this region when we got very, very close to extremality? Now, even for the neutral particle calculation that Hawking did, we actually know that there is a problem as the black hole approaches extremality. Namely, Preskill and collaborators observed in the 90s that close to extremality, there is a semi-classical breakdown of thermodynamics. How can one see this breakdown? Well, for that, it's good to compare the energy that the black hole has above extremality against its temperature. It's good to compare that to the average energy of a single Hawking quantum that such a black hole emits, assuming that the approximation of quantum field theory on a curve fixed background is valid. So in that approximation, Hawking found that the average energy of a Hawking quantum is roughly given by the temperature of the black hole itself. That's because the radiation is roughly thermal even when including gray body factors. However, if you look at how the energy above extremality behaves for a black hole as a function of its temperature, you'll find that it behaves quadratically with the temperature with a coefficient that's given by a scale that I'll call the breakdown scale. This breakdown scale for the charged black holes that I showed previously roughly goes like m Planck divided by q cubed. So for a black hole with a very large charge, it's a very, very small energy above extremality. You could also say that it's a polynomial in the entropy of the black hole. Sorry, it's 1 over a polynomial in the entropy of the black hole. And when the black hole reaches these energy scales, we see that these two curves intersect. So what happens when these two curves intersect? Well, in principle, below this energy scale, if the black hole emits even a single Hawking quantum, then the black hole will lose all the energy that it has above extremality, and we would end up, at least hypothetically, due to mass conservation, we would end up with a solution that is super extremal. And a solution that is super extremal is non-physical because it has a naked singularity. So naively, if I were to trust Hawking's calculation, namely the calculation of a quantum field theory on a fixed black hole background, I would conclude that something very bad happens towards extremality, and namely that the thermodynamics of the black hole seems to break down. For a long time, people realized that there should be some sort of effect that modifies this behavior of the black hole. And there had been proposal in string constructions of the black hole, in stringy constructions of black holes in supergravity for, what modifies this behavior. However, those calculations that were done in the 90s were not entirely under control because they were done in a weak coupling regime. While to really study this effect, you have to go into a regime of strong coupling in string theory where the gravitational description is valid. So more recently, we realized that the resolution to this puzzles comes from the fact that comes from quantum gravity effects. So specifically, one can really try to probe whether the assumption that we need to do the calculation of a QFT on a fixed black hole background is correct or not. And to do that, we can start out with our black hole metric and perturb it by some arbitrary perturbation in the metric that I'll denote by h mu nu. For most perturbations, it turns out that the standard deviation of most metric perturbations is fully suppressed by the entropy of the black hole itself. However, there's a special set of modes of the metric, which roughly speaking correspond to large diffeomorphisms in the near horizon region of the black hole, that turn out to carry a weight that's proportional to the temperature of the black hole when looking at the quadratic expansion of the Einstein-Maxwell action. So there's an infinite set of modes of the metric that become very, very light as we approach extremality. Now, whenever a set of modes in the quadratic expansion of an action become light, this means that we need to be very careful about how we apply our saddle point approximation because quantum effects could start overwhelming the answer that we get from our saddle point approximation. Usually, in the saddle point approximation, we assume that all loop effects are suppressed. But if we get the set of modes for which loops are not suppressed, then we're in trouble when applying the saddle point approximation. So what describes this set of metric perturbations? If I go to higher and higher orders in these metric perturbations when expanding the Einstein-Maxwell action. Well, it turns out that if I go to higher and higher orders in the expansion of the Einstein-Maxwell action, what you'll recover, and if you parameterize the set of metric modes by some function f of tau, it turns out that you could recast these perturbations as a set of modes described by what's called the Schwarzian theory that's given by an action that's an action whose Lagrangian is given by the Schwarzian derivative. That's a third derivative action in this function f. Now, interestingly, the coupling of this action is given by precisely the energy scale E breakdown that we encountered earlier. It was the energy scale at which we expected the thermodynamics of the black hole to break down. This theory becomes strongly coupled as we go towards low temperatures. And in principle, we would be in trouble understanding what happens to black holes if we didn't know how to quantize this theory. Now, luckily, this theory can be exactly quantized through a variety of methods. And one can actually account for all metric and field perturbations around the black hole background to obtain the corrected thermodynamic behavior of the black hole. So this can be seen if one computes, for instance, the partition function of the black hole. So if you can look at the partition function in the presence of these corrections, you see three terms, and I'll go through them one by one. The last term is just Hawking's answer that comes from the saddle point approximation itself. So this term um, at low temperatures is just the on-shell action of these black hole solutions. The next term, which goes like the area of the black hole to some power, the power itself is non-universal and it depends on the matter content of the quantum field theory that is coupled to the black hole. This is given by metric fluctuations and massless field fluctuations on top of the black hole background, whose standard deviation is roughly of order 1 over the entropy of the black hole. And because these fields and their quadratic expansion, the quadratic terms are suppressed in the entropy of the black hole, this coefficient is very small compared to the saddle point contribution, the on-shell action itself. People have actually determined what these coefficients are for our own universe and for gravity coupled to the standard model. One finds that this coefficient is minus 57 over 10. But nevertheless, this coefficient is subleading compared to this exponential term. The final term appears because of these large quantum fluctuations for the metric modes that are captured by the Schwarzian that we analyzed earlier. And this term is given by a power law in the temperature. And this coefficient of 3/2 that gives the coefficient of the temperature in the partition function turns out to be universal and is controlled by the fact that in the near horizon region of extremal black holes, there is an additional conformal symmetry that captures the number of zero modes in the Schwarzian action that we shouldn't integrate over. So this is the origin of this coefficient, and it's the same regardless of the matter content the matter content of the theory that we coupled to gravity. Now, the important thing about this effect is that you see that as the temperature becomes smaller and smaller, this term can overwhelm the answer that comes from the saddle point approximation. And eventually, the partition function at very, very low temperatures can become very small. Semi-classically, the partition function at very large low temperatures would be exponentially large, but because of this term, it can become very small. So this can be better seen if instead of looking at the partition function of the black hole, we look at the density of states of the black hole. So the dotted red curve represents the density of states of a non-supersymmetric black hole if one neglects the presence of these modes that has large quantum fluctuations. So this is basically the calculation that people did in the past. Now, if one accounts for these modes that have large quantum fluctuations, one finds that a deviation between the density of states that appears precisely at the breakdown scale at which we expect the thermodynamics of the black hole to be modified. And that's what we see. As the energy of the black hole approaches extremality, we see the density of states vanishing. So the Bekenstein-Hawking formula, Bekenstein-Hawking entropy formula, gets drastically modified at small energies at small temperatures. So the take-home message from these first slides is that the extremal black hole solutions that we learn about in GR are not good classical solutions, actually. And that's because they have enormously large quantum fluctuations. What we mean by a good classical solution typically is that it's a solution that really is dominant in the saddle point approximation with all other fluctuations being suppressed, all other loops with loop fluctuations being suppressed. The this modification of the black hole thermodynamics due to quantum gravity corrections also hints towards a resolution of the puzzle that I posed towards the beginning of the talk. So if you look at the average energy of the black hole above extremality, you see that instead of it behaving quadratically and having energies at which the energy of a single Hawking quantum is lower than the energy of the black hole, you see that once you include these large quantum fluctuations, the curve gets modified from the red to the purple curve, which behaves linearly at small temperatures above extremality. So in principle, this plot is meant to show you that the energy of that a black hole has above extremality is actually higher than the energy of a single Hawking quantum. But this plot is a bit of a cartoon because it still assumes that the energy of a single Hawking quantum is roughly proportional to the temperature, and we don't know, we don't have a reason for why this calculation is correct, because that calculation assumes that quantum gravity fluctuations are small. So we can now ask, how is the spectrum of Hawking radiation affected when one goes to extremality? And in order to do that, one has to couple to these set of modes that has large quantum fluctuations, the possible particle excitations that are emitted by the black hole. So depending on when the black hole emits, you can try to understand how a scalar, a graviton, or a photon that's being emitted by the black hole couples to these Schwarzian modes. And that will give you how the rate of Hawking, how the Hawking radiation rate is modified as we approach extremality. Now, I won't go into the details of this coupling, but if you're interested, please ask me after the talk. So if you, for instance, look at neutral particles, the simplest example of a neutral particle would be a massless scalar field that does not exist in our own universe. You can see that if the energy that the black hole has above extremality, which I'll denote by EI, if that energy is very large compared to the breakdown scale, the Schwarzian corrected answer and the semi-classical answer roughly agree. Now, on the other hand, if the energy above extremality is much smaller than the breakdown scale, so here is an example where the energy is zero point 0.1 of the breakdown scale, you'll find that the quantum corrected spectrum is drastically different than a thermal spectrum, than the semi-classically predicted spectrum. And perhaps its most important feature is that the spectrum is cut off at some frequency omega that's equal to the initial energy of the black hole. So this implies that a black hole can never go below extremality due to the emission of Hawking radiation, and that's because that emission is corrected by these quantum gravity effects, and because the emission, the emitted particle itself, back reacts on the space-time after it gets emitted. So this is what saves the black hole from going below extremality, and this is what resolves the puzzle that Preskill and collaborators posed in the 90s. So in our own universe, we don't have massless scalars. We instead have massless photons and gravitons that provide the dominant evaporation channel. And the issue with photons and gravitons is that we cannot ignore the angular momentum of the black hole when we consider the evaporation of such particles. And that's because such particles also carry away some of the angular momentum of the black hole. And if the black hole has different extremality bounds when its angular momentum J is slightly different, then we can see selection rules in the emissions of these particles that are somewhat reminiscent of the selection rules that we learn about during our undergraduate time in atomic physics. So, for instance, if I start out with a black hole that has this rough energy above extremality, and it emits a photon. Because the photon is a spin one particle, Then the resulting black hole is forced to either have angular momentum 2, 1, or 0 after the evaporation of the photon. Now, I should say that here you can actually derive these selection rules explicitly by looking at how the particles couple, how the particles that get emitted, the photons, couple to modes of the metric that have large fluctuations. So you could actually derive these selection rules. But the important thing that you can see is that, for instance, if the density of states close to extremality in the sector with j equal 2 is much lower than what the semi-classically predicted, then the emission channel from j equal 1 to j equal 2 will be very much suppressed compared to the semi-classical estimate. So you could see that, for example, if we start out with a black hole that has angular momentum 10. If you start out with a black hole that has angular momentum 10, if it has an energy above extremality that's much bigger than the breakdown scale, then the semi-classical rates and the quantum rates roughly agree. And you only see a small splitting between the different channels of evaporation. So here I plotted the channels of evaporation when you start out with a black hole with angular momentum J, and you end up with a black hole with angular momentum J prime that's either 9, 10, or 11. The lowest curve is 9 and the highest curve is 11. Oh, sorry, the other way. The lowest curve is 11 and the highest curve is 9. Great. Now, if the black hole, as the black hole gets closer and closer to the extremal bound in the j equals 0 sector, what we see is that some of these channels become completely disallowed. So, for instance, the transition from j equal 10 to j prime equal 11 can become completely disallowed. And the transition from 10 to itself is highly suppressed, and the quantum corrected spectrum only sees a transition from j equal 10 to j prime equal 9. That is very different than the semi-classical estimate. And this gives an even more extreme implication once the black hole ends up in a sector with zero angular momentum at an energy E that is roughly below E breakdown over 2, I believe. When that happens, when the black hole is here, because there are no other black holes that have J different than 0, at that energy level, we cannot emit even a single photon because of these selection rules. And this is analogous to what people encounter in the hydrogen atom when looking at the 2s to 1s transition of the hydrogen atom. So in the 2s to 1s transition of the hydrogen atom, all the other excited energy levels have an energy above 2s. So in order to preserve angular momentum, the atom would have to emit a photon and increase its energy, which is, of course, impossible. Now, as in the case of atomic physics, it turns out that this transition is possible not by emitting a single particle, but by emitting entangled pairs of particles. So the only way in which the black hole can lower its energy is if it emits an entangled set of photons that are in a singlet state. They need to be in a singlet state in order to preserve angular momentum. Now, it turns out that one can actually compute the evaporation rate into such a channel by going to next order in perturbation theory. So when you couple the Schwarzian modes to the fields to the photon field, to compute the previous rates that I show, you have to expand that action to first order in perturbation theory in the gray body factor of the photon. To see this effect, you have to go to next order in perturbation theory. Going to next order in perturbation theory leads to an extreme suppression compared to the previous rates that I showed before. So this all assumed that black holes were bosonic. But if the black hole was instead fermionic, by which I mean that it has a half integer spin, the selection rules are different. And for instance, it can always emit photons, even if the black hole ends up in the angular momentum sector that has lowest energy, which is J equal half. And that's because we can always go from a state with J equal half back to a state with J equal half for the emission of a single photon. And perhaps, as far as I'm aware, this type of channel doesn't have a good analog in atomic physics. So, for more complicated reasons, the emission rate into charged particles turns out to be unaffected by quantum gravity corrections. So, it turns out that the back of the envelope calculation that I showed by just using Schwinger's formula for pair production is actually correct, even when including these quantum gravity corrections. So, when you put these results together, they offer a complete history of black hole evaporation. So if you start out with the black hole that's somewhere in the MQ plane and you let it evaporate, it will emit neutral particles. Eventually, the black hole will go below the energy scale E breakdown, at which quantum gravity effects become important. And the dominant evaporation channel will consist of entangled pairs of photons. And occasionally, exponentially rarely, the black hole will emit an electron. An electron is fermionic. So if I start out with a bosonic black hole, I'll end up with a fermionic black hole after emission. Now, it turns out that because of the electric field of the black hole, the electron is comes out very accelerated at infinity. And the mass of the new mass of the black hole is actually different than what you might naively expect, which is the mass of the black hole minus the mass of the electron. Rather, it's an energy scale that's much closer to extremality, but it's still much above the breakdown scale that I mentioned previously. So after the emission of a single electron, the black hole still behaves semi-classically. It keeps emitting neutral particles, and eventually it will still enter a regime in which quantum corrections will become important. But this time, since the black hole is fermionic, it will have the ability to emit single photons, and the evaporation rate will be much faster. So it will actually get much closer to extremality in these fermionic eras. And then it will keep emitting an electron, and this process will repeat over and over again until it will get to the charge scale that's given by 10 to the 44 coulombs. And at that point, the Schwinger pair production rate will no longer be suppressed, and the black hole will slowly go away from extremality. And from that point onwards, we can actually trust Hawking's calculation for black hole evaporation all the way to the point when the black hole becomes Planck scale. Like the mass of the black hole is several times the Planck scale, at which point we don't know what happens because our effective theory completely breaks down. In all this process that I showed, it's of course an unrealistic process because in our own universe, black holes cannot be left in isolation. They have matter surrounding them, at least astrophysical black holes. But one important point is that the evaporation of these black holes take an enormous amount of time. So if you want to detect the quantum gravity corrections by looking at the spectrum by looking at the Hawking spectrum of these hypothetical black holes, that would take a lot of patience because individual photons would be emitted very rarely. So to actually make something that looks like a histogram of these emission rates would be enormously difficult. Now, one can instead take a black hole that for some reason is close to extremality, and instead of waiting for the black hole to evaporate, one can scatter off particles from the black hole. And then one can measure what the absorption cross-section of such particles is. So this was recently analyzed by Roberto and Paran using similar techniques to the ones that we developed to study black hole evaporation. And he found that the absorption cross-section for a scalar field in a near extremal black background in the near extremal black hole gets drastically modified when we get close to extremality. So semi-classically, the absorption cross-section of a black hole is roughly given by the area of the black hole itself. So this is why the semi-classical answer is roughly 1. Um, but as we go towards extremality, one finds that actually this absorption cross-section blows up, and eventually, exactly at extremality, it becomes infinite, meaning that it's actually very, very easy for the black hole to absorb these particles that have low energy that are being scattered off the black hole. So here you're seeing the absorption cross-section as a function of frequency. And just to mention, these kinks correspond to the fact that when the frequency of the particle that we send in is higher than the initial energy of the black hole, such particles can no longer be emitted, they can only be absorbed, and the absorption cross-section captures a linear combination of the two. So this discontinuity is comes from the fact that these types of particles can no longer be emitted. Um, Now, all these results are applicable for black holes and gravity with some arbitrary matter content. I assumed in the previous slides that the matter content is given by the standard model, but how about black holes in supergravity? Famously, in string theory, we have counted the number of extremal black hole microstates. And the results that I showed earlier suggest that the density of states close to extremality for black holes actually vanishes. And that would seem in tension with the results from string theory, in which the exact count gives a number that's exponentially large in the area over G Newton. So for black holes in string theory, we should really see that the density of states is very large at extremality. So what we did previously has to be corrected. And the reason why it gets corrected is because in the black holes whose entropy was explicitly counted in string theory are not black holes in ordinary theories of gravity. They're black holes in theories of supergravity, and more specifically, they're BPS black holes. And in theories of supergravity, there's not only a graviton whose fluctuation we need to worry about, but we also need to worry about possible quantum fluctuations of its supersymmetric partner, the gravitino. And specifically, if you take a supergravity action, let's say n equal to 2 supergravity in 4D flat space, and you do the quadratic expansion of the action that I mentioned previously, you'll find that there's not only a light sets of modes for the metric, but rather if the black hole is close to the BPS bound, there's also a light set of fluctuations for the gravitino that have exactly the same coupling. Namely, they have a quadratic weight that is proportional to the temperature of the black hole divided by the breakdown scale. And this completely alters the low temperature behavior of the black hole. Now, the action of these modes is actually described not by the ordinary Schwarzian theory, but rather if you go to higher and higher order in the mode expansion for the graviton and gravitino, what you'll find is a supersymmetric version of the Schwarzian theory called the n equal 4 super Schwarzian, which here I wrote the bosonic part of the n equal 4 super Schwarzian, consists of the Schwarzian derivative coupled to a field G that parameterizes the rotation of the black hole. This G is valued in SU2. It's a group element of SU2. If you symmetrize this, supersymmetrize this action, you get the n equal 4 super Schwarzian. Now, just like the ordinary Schwarzian, it turns out that this is a theory that can be quantized exactly. And we did that a couple of years ago to obtain what the density of states of black holes and theories of supergravity are. Yes. So here you see the density of states compared to the exact density of states, which I show in purple, compared to the semi-classical density of states, which is the dotted red curve. Now, the dotted red curve in a theory of supergravity looks almost identical to what you saw in a conventional gravitational theory, and that's because the black hole saddles in supergravity and gravity pretty much look the same. Like if you open a supergravity book or you open an ordinary GR book, you'll pretty much find the same solutions in which all fermionic fields are turned off. However, when you take these quantum fluctuations into account, you find that the density of states for black holes in supergravity is drastically different than that of black holes in theories of gravity. Namely, you find a large degeneracy at extremality, which is perfectly consistent with the count from string theory, followed by a gap. This is actually a gap that was conjectured in string constructions of the black hole by Maldacena, Strominger, and Susskind. And the order of the gap, which turns out to be breakdown over 8, exactly agrees with the stringy construction of these black holes. Now, above the gap, what we find is a continuous density of states that has this small kink. Let me explain what that kink is, because it will turn out to be important. So here I plotted the density of states of black holes with zero angular momentum. But perhaps a better plot is if we showed the density of states of the black holes that arrange itself in different black hole supermultiplets. And this is what I've shown here. So the BPS black holes turn out, all the states that are BPS turn out to have angular momentum 0. So this is the only BPS multiplet in the theory. It just consists of states that have J equals 0. Above that, there's a multiplet that contains black holes with spin j equal half and spin j equals 0. And above that, there are black holes that are in a supermultiplet that contains black holes with 0 angular momentum half, and angular momentum 1. So this kink that you see in the previous plot is due to the fact that here, at this point, we see at the point where the kink appears, we see the appearance of a new supermultiplet in which black holes are also allowed to have angular momentum 1. So I'll denote the states within within a supermultiplet. There are 4 states within a supermultiplet. I'll denote them by H, psi, chi, and L. Now, just as a small observation, um, even though the entropy of the black hole is roughly given by the area over 4G Newton at extremality, this is a coincidence. And what I mean by that is that the extremal solution still has very large quantum corrections that can be seen in other observables. And as we will see, they can be seen in the spectrum of Hawking radiation. So the saddle point, the fact that the entropy is equal to area over 4G Newton doesn't imply that the saddle point is reliable any more than it was in the ordinary theory of gravity. So this brings me to the evaporation of black holes in supergravity. So in supergravity and flat space, all Hawking emission drives the black hole towards its BPS bound. And this is because if supersymmetry is unbroken, all particles satisfy the BPS bound. And in particular, this implies that there's no particle that will help the black hole lose charge faster than it loses mass. So in contrast with the non-supersymmetric case, the BPS black hole will actually be the final state of evaporation. So in the non-supersymmetric case, we saw that the black hole goes through this process of zigzagging very close to the extremality bound, and eventually it departs once it gets to 10 to the 44 coulombs. It departs that it changes that behavior, and eventually the black hole reaches Planck scale, at which point we don't know what happens, but perhaps we expect, if we don't expect black remnants, we expect the black hole to fully evaporate after that point. In contrast, in supergravity, it's possible to end up with extremely long-lived BPS black hole as the final state of evaporation. Now, I should mention, since this oftentimes appear as a point of confusion, that the final state, even though the black hole is BPS, the final state is non-BPS. And this is because we should think about the final state as being that of the black hole, which is an object that is BPS. And very far away from the black hole, we have all the particles that it has emitted. Um, that are possibly still entangled with the set of BPS black holes. And because those particles themselves might not be BPS, the final state is and are moving relative to the black hole. That final state is not explicitly BPS. So we're not saying that we start out with a non-BPS state and we end up with an overall BPS state. We're just saying that you end up with a BPS black hole. Starting with a BPS state and ending with a BPS state would be impossible through unitary time evolution in a theory of supergravity. So for simplicity, we will focus on the radiation emitted through a massless scalar field. And the black hole that starts in the state psi, this was one of the states in the supermultiplet, that has angular momentum 0. And as before, you can see that depending on what energy you have above extremality, what initial energy you have above extremality, the semi-classical rate can be drastically different than the quantum corrected rate. And in particular, if you are 1,000 times above the breakdown scale, then you'll see that the semi-classical rate and the quantum rate roughly agree. And they also roughly agree with the result that you would get in the non-supersymmetric theory. Now, once you get closer to the breakdown scale, you see that the quantum rate and semi-classical rate start differing. And in particular, you also see that when you take these quantum corrections into account, you can very explicitly see how the black hole transitions into various members of a supermultiplet that also would have J equals 0. So a black hole that starts out in the state psi can stay in the state psi, but it could also transition to a different supermultiplet that is chi or L, a different member of a supermultiplet. Now, the most interesting transition, perhaps, is the one where this state psi doesn't transition into a non-BPS state, but transitions directly into a BPS black hole state. And the reason why that's interesting is because you see that these transitions are completely separated. The spectrum of those transitions are completely separated from the transition into non-BPS states. So these transitions from the psi state to the BPS state appear as discrete emission lines in the spectrum of Hawking radiation. And these discrete emission lines are simply due to the fact that the black hole spectrum has a gap that's given by the scale E breakdown over 8. So when you consider a transition rate from a black hole all the way directly to BPS, it's impossible to evaporate or to emit particles that have frequencies in between your initial energy minus E breakdown over 8 and the initial energy itself. So this is the gap that you're seeing. This gap is exactly equal to this gap, which is E breakdown over 8. So as before, these new quantum gravity effects drastically affect the spectrum of Hawking radiation at very low temperatures and lead to the first emission line for that we've seen for black holes from the gravity path integral alone. So this also allows us to explicitly see how a supersymmetric black hole evaporates over time if it starts out in the psi state above extremality. Then eventually the black hole will slowly evaporate into BPS states and non-BPS states. And if you wait for longer and longer, you'll see that these non-BPS states themselves will transition will transition further down into BPS states. So here you're seeing that the probability of finding a non-BPS state decreases over time. And eventually, if you wait for a very, very, very long time, you'll see that the black hole ends up fully in the BPS state. Now, just as before, in a theory of supergravity, we could also analyze what happens if we scatter particles off black holes. So instead of waiting for the black hole to evaporate, we could take these hypothetical black holes and scatter the massless scalar that we were studying previously off it. And the absorption cross section turns out to be very complicated as a function of the frequency above of the frequency that the scalar has. And you see all of these sharp kinks in the absorption cross section. I won't go into each individual sharp kink, but rather I'll just say that each sharp kink corresponds to either the appearance or disappearance of a possible emission channel into a certain member of a supermultiplet. So for instance, the kinks to the right, these ones over here, occur exactly when the frequency of the black hole omega is the initial energy minus E breakdown over 8. And that's precisely the last energy at which the black hole can actually emit any scalar excitation that wouldn't end up in the BPS state. Now, exactly at the BPS state, we see a sharp jump in the absorption cross-section, and that corresponds to the fact that when the frequency of the scalar is exactly equal to the initial energy, there's a direct sorry, there can be a direct emission from the black hole that has energy EI all the way down to the BPS state. Now, the plot on the left assumes that we start out with a black hole that's non-BPS and scatter particles from it. If we instead start out with a particle that is BPS and scatter particles from it, we find very interestingly that there is a region of non-zero omega where the black hole is completely transparent. And that exactly corresponds to the fact that the spectrum of the black hole is gapped in that region. And that's exactly what we would see if we tried to scatter photons off atoms that have discretized energy levels. We would see that if the frequency of the photon doesn't match on the energy difference between the current energy of an atom and the energy of some excited state, then that photon could not be absorbed by the atom. At very low frequencies, BPS black holes are transparent, and that's a new phenomenon that's due to quantum gravity effects. Now, eventually, the absorption cross-section grows much above the semi-classical estimate, and then eventually, at very, very high frequencies, it goes towards the semi-classical estimate from by neglecting these when you neglect these quantum gravity corrections. Great. So to summarize, charged black holes with large enough charge get incredibly close to extremality when left to evaporate in vacuum. Close to extremality, quantum corrections drastically affect the rate of Hawking radiation for neutral particles, but don't have a big effect on charged particles. But these corrections alter the history of a black hole and what even the simplest observables, such as the temperature seen by a thermometer far away from the black hole. And for supersymmetric black holes, the story is even crazier. Namely, the spectrum of radiation has discrete emission lines, just like the ones that we see in atomic physics. And since I'm a little bit over time, I'm just going to leave you with this final set of questions that we plan to pursue in future work. Thank you very much. Any questions?
Thanks very much, Luca, for this very nice talk. Thank you. Questions,
Thank you
yeah,
as well.
questions.